This is a lesson on part 2 of the photoelectric effect. So in the previous lesson I introduced the photoelectric effect, which is basically where you've got a hunk of metal, and you've got light of a specific frequency that's greater than some threshold frequency, f sub naught. And I should mention the light in this picture is coming in as little packets called photons, and what you get is emission of electrons from the metal surface. This is the photoelectric effect. Albert Einstein in 1905 made 3 assumptions to explain what was happening. So electrons, the first assumption was that light consists of photons, each with energy E equals hf, where E is the energy in joules, h is Planck's constant, a number 6.626 times 10 to the minus 34 joule seconds, and f is the frequency of light in hertz. Einstein's second assumption was that there's this one-to-one interaction between a photon and an electron. In other words, for every photon coming in, there's one electron coming out. Okay, due to energy conservation, whatever comes in has to come out. Number 3, there was a specific amount of energy, known as the work function phi, needed to eject an electron from the surface of the metal. And different metals have different work functions, okay, due to how the electrons move, how fast they move, how closely bonded they are to their nuclei, and so on and so forth. So Einstein also, he applied the law of conservation of energy, okay, for the one-to-one interaction between a photon and an electron. So a photon is given by the symbol gamma, lowercase gamma, Greek letter gamma. Law of conservation of energy. So hf sub naught is equal to the work function phi. So a photon of some specific amount of energy, hf sub naught, equals some energy to escape the surface. So you need some energy coming in to result in energy, enough energy for an electron to escape the surface. So that's the law of conservation of energy. Whatever comes in has to come out, in other words. Now the energy of an incident photon, we can write an expression. Energy of an incident photon is equal to the energy to release an electron plus the maximum kinetic energy of the released electron. In other words, hf is equal to phi, some work function, plus the maximum kinetic energy of a released electron. Okay, statement of conservation of energy once again. So photon coming in, hits the surface, electron is able to escape to the surface. Okay, so think of the electrons sitting down at the bottom of the hunk of metal. Once it hits the surface, that's the energy phi, that's the work function, energy needed to help the electron escape, plus some kinetic energy associated with the electron. So the electron has, you can think of it as 2 energies, right? One for it to be released from the surface, and the other, its kinetic energy, its moving energy associated with the transition. So in other words, we can express the kinetic energy, the maximum kinetic energy of the released electron, as hf minus phi by rearranging the top expression. And you can plot the maximum kinetic energy of the photoelectrons with the incident light energy, hf sub naught. Okay, and there's 0. What you'll find is that different metals, metal X, let's call it metal X, metal Y, metal Z. Different metals have different work functions, and hence different maximum kinetic energy values of the photoelectrons. Apologies, I'm going to get rid of the H here. The threshold frequency, right? And for any metal, you should get a straight line, okay, with a gradient equal to Planck's constant, H. Okay, in other words, the slope is equal to H. because this is the equation for a straight line. Think of y equals mx minus b. Right. Where m is the gradient, okay, and m in this case is h. And the y-intercept is phi, so if you extend these graphs down, these straight lines down, you'll hit the y-axis. That tells you the maximum kinetic energy of the photoelectrons. So this was actually experimentally verified by an American physicist named Robert Millikan in 1916 at the University of Chicago. And ironically, he spent 10 years of his life trying to disprove Einstein's idea. Okay, so Millikan was a hardcore classical physicist, and ironically ended up winning the Nobel Prize for his work, amazingly. So this was Millikan's setup. He had two electrodes. He had a negatively charged plate, positively charged plate, okay, connected to a voltmeter, and a variable power supply. A variable power supply is basically power supply enabling you to adjust the voltage, output voltage and current if necessary, and an ammeter. Okay, so if you recall, an ammeter is connected in series and a voltmeter is always connected in parallel. So these two electrodes were housed in a casing, particular casing. Light was incident, so you had like a quartz window that absorbs high energy, high frequency light like UV. So it was enabling the light to pass through, hit the negative electrode, and the negative electrode would emit electrons and they would head towards the positive electrode, right? Because negative and positive attract. And all the photoelectrons would be attracted to the positive electrode, and then the ammeter A records the maximum photocurrent measured. Now, if however the negative and the positives, I should say the positive electrode became negative, the photocurrent that's measured will decrease, because the photoelectrons will then be repelled by the electric field between the two plates. And so the initial kinetic energy of most of the energetic photoelectrons, so initial kinetic energy of the photoelectrons will be equal to the work done by the electric field to stop it. Okay, in other words, the maximum kinetic energy of the photoelectrons is equal to the work done, which is Q, the charge of the electron, times V, okay, otherwise known as the stopping voltage. Okay, the minimum applied voltage required to reduce the current to zero. Right, and Q is just a number. It's 1.602 times 10 to the minus 19 coulombs. I should say minus. And so we can therefore calculate the maximum kinetic energy of the photoelectrons by measuring the stopping voltage, V sub stop. That'll decrease the current to zero. So I'll explain that again. Suppose the positive plate became negative. In other words, you swapped the positive and negative plates. The photoelectrons will be repelled by the negative plate. Okay. I should say, my apologies. The positive plate, suppose it became negative, the electrons will be repelled. Okay, because negative and negative repel. And so, therefore, you would need, therefore, there'll be work done on the electrons to stop them from reaching that negative plate given by QV. And that voltage, the minimum, the voltage that's applied for that to happen is called the stopping voltage. And just a note, photocurrent increases with incident light intensity. Okay, the more intense the light, the more current coming out, right? Because there's more photons coming in and hence more photoelectrons coming out. Let's do an example. Let's see how this works. Suppose you have a light source with wavelength equal to 600 nanometers and has power equal to 1 microwatt. What is the energy in electron volts of the emitted photons? So let's work this out. Okay, so first things first, let's work out the energy. So E equals HF from the Planck relation. Now that's also equal to HC over lambda. Plugging in values for H and C, they're just numbers, so 6.626 times 10 to the minus 34 for H, Planck's constant, times 3 times 10 to the 8 for the speed of light C. Wavelength, we're given lambda, which is just 600 nanometers, 600 times 10 to the minus 9 meters. Plugging these into a calculator, you'll get 3.13 times 10 to the minus 19 joules. Okay, the 2 decimal places. Now we need the answer in electron volts, so let's divide by 1.602 times 10 to the minus 19, because that's how many joules there are in 1 electron volt. That equals 1.95 times 10 to the minus 38 electron volts. Now let's suppose we were asked to find the maximum kinetic energy of the photoelectrons given a work function of 1 electron volt. So let's use the formula from before. Maximum kinetic energy of the photoelectrons is equal to the frequency of the light minus the work function. Frequency of light, we calculated it. Now in electron volts, it's 1.95 electron volts from before, 1.95 electron volts. Work function is given as 1 electron volt. So 1.95 minus 1 electron volt is simply 0.95 electron volts. So that's the maximum kinetic energy of the photoelectrons in terms of electron volts. And that's how the photoelectric effect works. The assumptions: light is made of photons with energy E equals HF. There's a one-to-one interaction between a photon and an electron. And there's some specific amount of energy, some work function phi, needed to eject electrons from the metal surface. And different metals have different work functions. So it's really using these basic ideas, these basic equations to find out what's happening and how to calculate different quantities for experiments involving the photoelectric effect.